Hi there. So we have seen the traditional approach for OpenGL. Now let's proceed to part 3, which is the modern approach for OpenGL. Now in this topic 2, part 3, we will look at the following content. We'll begin with some definition about the graphics processing unit, which is the GPU, followed by a simplified pipeline and architecture for this modern approach of OpenGL. And then we will look at what is vertex shader, the primitive assembly, the clipping and rasterization, and not forgetting the fragment shader, testing and blending, and then the detailed implementation for all these. The previous lecture, we have seen the fixed function pipeline, which I have categorized as the traditional approach. Now, this traditional approach mainly uses the GL utility library, which is GLU, and it provides additional high-level utilities which implements much of the linear algebra needed to move the objects on the screen. Today, we are going to look at the programmable pipeline, which I have categorized into modern approach. Now, this modern approach mainly uses shaders for the implementation, and the language they are using is called GLSL, or stands for OpenGL Shading Language. And besides that, they use extensively GLM, or OpenGL mathematics, to do some linear algebra. The world we live in is in three-dimensional. So in 3D graphics, we try to preserve this third dimension as much as possible. With computer graphics, this is done by modeling in 3 dimensions, with these models being built from meshes and textures. A mesh is actually a collection of vertices, edges, and faces, which resemble the real-life objects. To add realism, each surface of the faces is given some texture, which is nothing more than an image. As shown in this diagram, by now we have a representation of an object in 3D. By adding more objects, we can build the entire scene. And by letting the objects move, that will be a 3D animation. In the relevant software, the 3D models are represented by so-called vectors, and all calculations are conducted with vector calculus. However, computer displays can only output 2-dimensional images, and these images are built from pixels which are ordered in a raster. Such a 2D raster image is something else entirely to the 3D vector-based model. So, an important task of the graphics card is to transform 3D models into 2D raster images, which can then be the output to the display. Now, this process is what we call the 3D rendering process. Now let's take a look at the simplified version of the graphics architecture, which consists of the input, the CPU, the GPU, and finally the display. A CPU works together with a GPU in order to increase the throughput of data and the number of concurrent calculations within an application. GPUs were originally designed to create images for computer graphics and video game consoles. But since the early 2010s, GPU now can be used to accelerate calculations involving massive amount of data. Now, a CPU can never be fully replaced by a GPU. Now, why is that? A GPU complements CPU architecture by allowing repetitive calculations within an application to be run in parallel while the main program continues to run on the CPU. The CPU can be thought of as the taskmaster of the entire system, coordinating a wide range of general-purpose computing tasks, with the GPU performing a narrower range of more specialized tasks, usually mathematical. Using the power of parallelism, a GPU can complete more work in the same amount of time as compared to a CPU. So overall, GPU is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in the frame buffer, which intended for the output to a display device. It runs on the simple programs called the shaders, which actually take in vertices and other data. Now, since this unit has to do all the hard rendering work, it is essentially a CPU but with thousands of cores, as you can see in this diagram. This is an example for NVIDIA GeForce GTX 480 model. This is another diagram to illustrate what is inside a GPU. Now, the main difference between CPU and GPU architecture is that a CPU is designed to handle a wide range of tasks quickly, as measured by the CPU clock speed. But they are limited in the concurrency of tasks that can be running. While for GPU, it is designed to quickly render high-resolution images and video concurrently. Let's take a look at some examples of CPU to GPU computing. The first example is the rendering video. The graphics card helps transcode video from one graphics format to another faster than relying on a CPU. The second example is the accelerating data. A GPU has advanced calculation ability that accelerates the amount of data a CPU can process in a given amount of time. When there are specialized programs that require complex mathematical calculations, such as deep learning or machine learning, those calculations can be offloaded by the GPU. This frees up time and resources for the CPU to complete other tasks more efficiently. The last but not least, the cryptocurrency mining. Obtaining virtual currencies like Bitcoin includes using a computer as a relay for processing transactions. While a CPU can handle these tasks, a GPU on a graphics card can help the computer to generate currency much faster. During the lecture, I will actually show you a simplified OpenGL pipeline which composed of different stages, and every stage is specialized precisely on one element of the rendering process. Once we are familiar with these tasks, we will be able to recognize them in the designs of the GPU. That's the end of this video. I'll see you in the lecture. Bye.